Okay, guys. Okay, let's get our cameras on. Hopefully, there'll be some more showing up here. Let's get our cameras on. We've got what on Friday? We've got what on Friday?
Quest 2.
Quest 2. Quest 2. Now, Quest 2 will be a little bit of dot product, a little bit of dot product, a lot of cross product, a lot of cross product, and then what we do on lines today. What we do on lines today. I think I was looking through the flashcards. I think we should have about our first 47 or 48 flashcards made. We should have our first 47 or 48. That's what the quest mean. It'll be related to those 47 flashcards or 48 flashcards. I forget exactly which one. Okay. When I say line, you say. When I say line, you say. A plus TD. Okay, that will save you on Friday. That will save you on Friday. So I'm looking here. I've got my three basic forms of a line that I've written down. I've got my three basic forms of the line. My first one is called the vector form. And we're assuming that t, this scalar t, goes between minus infinity to infinity. T is allowed to take any value between minus infinity to infinity. And this is the form I want you guys just drilled into your head. A plus TD. So I've got a position vector at the origin. I've got a position vector at the origin. I've got the blue vector's the direction. Green is A, blue is D. And I scale D either this way or that way through infinity to minus infinity. And so my line runs right on top of my blue vector, all the way for forever and ever. Now, the first thing we realize is that lines are a myth. Lines are a myth in reality. Sure, they're geometric quantities, but you can't get a line in the universe. You can think of a spaceship traveling in a vacuum of space, but eventually some gravitational pull is going to pull on that thing. You're not going to be able to shoot it straight through. But it's a useful myth. It's a useful myth. The next form of the line is the symmetric form, the classic form before vectors. I call it the Descartes form of the line. If you have A plus TD, it's super simple. It's super simple to go to the symmetric form. It's x minus a1, the first component of your position vector, x minus a1 divided by d1, the first component in your direction vector. Then y minus a2 divided by d2, the second components in your position and the second component in your direction vectors. And z minus a3 equals z minus a3, and again, position vector, direction vector. So here's a line, and here's a line. Here are two lines. They're in my parametric form. Or what I call the space curve form. This is the thing that you would use to plot in your plotting programs. We say that R of t is equal to A1 plus TD1. That's the first component. The second component of my space curve is A2 plus TD2. And my third component is A3 plus TD3. But guys, if you already have 1, is it hard to get to 3? If you have 1, is it hard to get to 3? If you have 1, it's just vector addition and scalar multiplication. Okay, look at these two lines. I've got two lines here. Read the first line to me. What's the first line?
2 plus 5t.
2 plus 5t.
6 minus 4t.
6 minus 4t.
8 plus t.
Is it in the vector form, the parametric form, or the symmetric form?
Parametric.
The parametric form. I've got my second line. 2 minus 10t, and again in my space curve form, 2 minus 10t, 3 plus 8t, and the last component is 0, 0 minus 2t. The last component is 0 minus 2t. I want you to put both of those lines in the other two forms. I want you to put both of those lines in your symmetric form, and I want you to put it in your vector form, your a plus td form. You have those two lines, put them in your vector form and your symmetric form. Okay, you're now going to share what you have with other people. You're going to share what you have with other people. I'm a moron. I'm an idiot, I'm an idiot, I'm an idiot. I made too many breakout rooms. Now you're going to share. Okay, what do you have for the symmetric form of the first line? What do you have as this for the symmetric form of the first line?
X minus 2 over 5
X minus 2 over 5
equals y minus 6 over 4
equals y minus 6, not over 4, but over negative 4. Negative 4. Because the basic form has the, my D has the plus in it. Equals Z minus 8 over 1, which is equal to Z minus 8, which is equal to Z minus 8. Okay, what is the A plus TD form? What is the A plus TD form of the second line? What is the A plus TD form of the second line? What's the vector A? What's the vector A?
2, 6, 8.
To not 6, 8, but to,
Are we looking at the first one? Oh,
no, the second one, sorry.
Oh, okay, sorry. Then it'd be 2, 3, 0.
2, 3, 0. There's a position vector. It's laying in the xy plane. It's laying in the xy plane because you're not moving up. Then plus t times your direction vector. And what's your direction vector, guys? What's your direction vector? What's the direction vector for the second line?
-10, 8, -2.
-10, the thing multiplying the t. -10, 8, -2. -10, 8, -2. How many people think they can do this on Friday? How many people think if I gave you 2 lines, you could go between the 2 forms? Okay, really the only way to learn to do it is by doing it. Doing your homework. That's the only way you're actually going to learn how to do it, is by doing your homework and comparing with the back of the book. Okay, now what I want you guys to do is I want you to go open up that plotting routine in announcements. Go to announcements and open up that plotting routine, and I'm going to do the same thing. I'm going to do the same thing. Okay. Share my screen. Okay, so now I'll go to announcements. I'm going to go to Easy Plotter. I'll click on this. The first thing I want to do is get rid of this stupid space sheet. So I've got rid of that. The next thing I want you to do is click on that blue box. Click on that blue box and change this to 10, change all of these to 10, and change these to 2. So the first thing you do is change all these to 10, minus 10, minus 10 to 10, minus 10 to 10, minus 10 to 10, and all of these tick marks at 2. So that's going to be the first thing I'm going to do. And you go ahead and do the same thing. I know you can probably use tab. I don't. When you're done with that, just hit graph. Come up here and hit graph. So when you're done with that, just hit graph. And there you can see your 3-dimensional space. You can see your coordinate system there. All right, the next thing, I'm coming out of the cave. I'm coming to the front of the room where I can talk to the mic. The next thing I want us to do is to plot those 2 space curves. The next thing we're going to do is plot the 2 space curves that represent the line. Now again, for those who are, R1 of t is 2 plus 5t, 6 minus 4t, 8 plus t. R2 of t is 2 minus 10t, 3 plus 8t, and minus 2t. So now, let's go to the drop-down menu for select. And it gives me a bunch of options. We're picking space curve. And then what I want to do is I want to put, this will be R1. So in x of t, I'm going to put 2 plus 5t. What do you think is going to go in the next line? What do you think is going to go in the y of t? If you had to guess, what do you think is going to go in the y of t? 6 minus 4t. And then in the last one, I 8 plus t. Now go down here and click on primary color. If you look down here, let's make this, red works for me. Now let's just plot our line, and then you can move it around. So there's my line sitting here in three-dimensional space. Here's my first line sitting in three-dimensional space. Now I'm going to put another line in. Now I'm going to put another line in. I'm going to hit select, another space curve. Now I don't know why it's changing this. I want my parameter running between -10 and 10, not 2 pi. Now here, I want 2 minus 10t. Three plus 8t. And minus 2t. I'm gonna again use a primary color like blue. I'll take blue. And then I'll click here to make it visible. And so there's my lines. There's my lines in three-dimensional space. There's my lines in three-dimensional space. Now, if you look at those lines, do they look like they intersect? Do those lines look like they intersect to you? Do they look like they intersect? And you're like, Dr. Warren, that's kind of hard, just plotting them to determine whether or not they're going to intersect. Do they look parallel? Do they look parallel at all to you? I mean, if we roll them around, do they look parallel at all? Whoa, that's fun. Okay, so in the classroom, I've actually got some lines. Let me put them up here for us. Here's one line. And here's my other line. I want this one to go over. Okay. Now it's a little hard for you guys to see because you're not in the space with us. In the same way, it's a little hard to see on those plotting routines. If you have two lines, they could either be parallel. These are not parallel. Look at me, look at me, look at me. They are not parallel. These do not intersect. They may look like they intersect to you, but there's actually this much distance between them. There's that much distance between them in here. Write this down, write this down. In general, lines in three-dimensional space don't intersect. Kids get confused by this. They're used to planes where they have to intersect. In general, in three-dimensional space, two lines rarely intersect. These lines are not parallel. These lines are not parallel. One's shooting this way through the room, and the other's shooting this way. If I look straight down on them, they kind of look like they're making an X. When two lines do not intersect, and they're not parallel, we call them skew. S-K-E-W. Skew. So my two lines in my classroom, my brown line and my blue line, are skew lines. They're skew. Now ask me, Dr. Warren, how do I know if two lines are parallel? Ask me that. How do I know if two lines are parallel?
How do you know if two lines are parallel?
Okay, thanks, Michael. That's good. How do I know if two lines are parallel? Okay, listen up. Two lines are parallel. Two lines are parallel. If this is L1 and this is L2, L1 is parallel to L2 if their two direction vectors are parallel. If their two direction vectors are parallel, then that's going to force your lines to be parallel. Now look at my lines here. Look at my lines here. Maybe the green vector is my direction vector. Maybe the green vector is my direction vector for the brown line. And my blue vector is the direction vector for the blue vector is my direction vector for my blue line. Do you see that they're not parallel? Visually, can you guys see in that fisheye that they're not parallel? Now, do you guys want to plot on Friday? Do you want to plot on Friday? Would you like to waste your time plotting, or would you like to have a flashcard that could help you determine whether or not two lines are parallel? How many people want a flashcard? I can't raise my hand. Raise your hand. Okay, good. Everybody's hands in the air. What's the easiest way to determine whether or not two vectors are parallel? It's not the definition that D1 is equal to alpha D2. What's the easiest way to determine if two vectors are parallel?
They're scalar multiples of each other?
If they're scalar multiples of each other, yeah, that's the definition, but that takes solving equations to do that. What's a simpler way? So imagine that I've got two vectors that are parallel. Imagine that I've got two vectors that are parallel. Okay? I've got two vectors that are parallel. And I'll just move them right on top of each other. So they're kind of hugging like this. They're kind of hugging like this. What if you take their cross product? What's the cross product of the blue vector and the green vector? What's the cross product of the blue vector and the green vector? Well, you're like, Dr. Warner, there's no way to swing. There's no way to swing. If you make it like this, where they're not parallel, then it's pretty easy. You just visualize it. You go, whoop, and it goes like that. It points up like that. But if they're right on top of each other, you're not going to have any area. Do you guys see that? There's no area. And we know that the norm of A cross B is the area of the parallelogram. But there ain't any parallelogram. So, write this down. If D1 cross D2 is zero vector, if the D1 cross D2, those two direction vectors are the zero vector, then what do I know about the two lines? What do I know about the two lines?
They're parallel.
They're parallel. And that's one of your flashcards. That's one of your flashcards. If D1 cross D2 is the zero vector, that means my two direction vectors are parallel, which in turn implies my two lines are parallel. Okay, now go to the two lines we have here that we just plotted. We've got this line and this line. Find the two direction vectors. Find your two direction vectors of those two lines. Find your two direction vectors of those two lines and take the cross product and see what you get. Take the two direction vectors of those two lines and take their cross product. Sadly, for sake of time, I've got to stop you. Sadly, for sake of time, I've got to stop you. Okay, this is the direction vector for the first line. D1 is 5, -4, 1. That's the direction vector. How many people had that? Raise your hands. How many people got that direction vector right? Okay, if not, you probably can see the mistake that you made. Direction vector number 2. Direction vector number 2 is -10, -10, 8, -2. How many people had that? How many people had that? -10, 8, -2. The question is, are they parallel? Well, you want to do D1 cross D2, and as long as any component is not 0, they're not parallel. I think the determinant method is the easiest for me to do, so that's what I did. I just put my IJK, I put my D1 here, my D2 there. I cover up this. -4 times -2 is 8. -8 times 1 is 8 minus 8, which is 0. And you're like, crap. If that wasn't 0, I could stop the problem and say they're not parallel. But I gotta move on. I do my J. I already have my minus there. I do my J. I do 5 minus 2, which is -10, minus -10 times 1, which is -10. And -10 minus -10 is 0. And you're like, crap, if that wasn't 0, I would be done. Now I look at the last one. And I'll get 40 minus 40 minus 40. And again, I get a 0. So what do I know about those two lines? They're parallel. Those are parallel lines. So now go back and look at the plot. Go back and look at that plot. Spin that plot around and look at those two parallel lines again. Go back and look at the plot and look at those parallel lines.
Professor Warren, is the angle between them 0? Does that have anything? Or?
The angle between them would be 0. Yeah, I mean there would be no angle between them. They're really, since they don't intersect, we don't really talk about an angle between them. If two lines intersect, we talk about the angle between them. But like if they don't intersect, like if they're skew, there isn't an angle between them. Okay, stand up again. Stand up. Stand up. You need to stand up. I can tell. You need to stand up. Stretch. Say, who's your mama? Say, who's your mama? Some of you didn't say it. Say, who's your mama? I know you aren't, but not by the space bar. Sit back down.
Dr. Warren,
Yes.
wouldn't it be easier to just see that you can multiply by -2?
You know, I think in general, that's not going to be easier. In this case, yes, it would be pretty simple to see that you could do that. But for some numbers, they'd be so big, it would be a little hard to see whether or not you would find the scalar that would do that. And so I think taking the cross product is one safe way to actually make sure that you're doing it right. That's just my idea. I don't care how you figure it out, as long as you can answer the question right, other than cheating. In general, two lines do not intersect. What did I say that? What did I just say? But if I give you two lines, do you want to have to try to plot them to determine whether or not they intersect? No. So ask Dr. Warren, how do I figure out if two lines intersect? It's miserable. It's miserable. Okay, so sit back. Grab your magic lasso. Grab your magic lasso. Grab your magic lasso. Grab your magic lasso. Okay, throw your magic lasso. Throw your magic lasso. Wrap up your attention span. Wrap up your attention span. I hope I didn't get COVID by this. Put that there. Okay. In general, it's pretty hard. In general, it's pretty hard to determine whether or not two lines intersect. On a test, it's a nightmare because it's a very, very time-consuming process. If I don't pick the numbers to make it easy, it's difficult to determine whether or not two lines intersect. I'm going to give you two lines, and I'm telling you right now, they are going to intersect. It's rare, but I'm going to force two lines to intersect. Now, let me give you your two lines. Let me erase these lines. Let me give you your two lines. Here's two lines that intersect. 4 plus 5t, I'm giving the parametric form. 4 plus 5t. The second component is 6. 0t. 7 minus 2t is the last component in the space curve for my line. My second line as a space curve is 6 minus 4t, negative 3 plus 3t, and negative 1 plus 4t. Now imagine you're on the test, and I ask, do these lines intersect? I could ask, are these lines parallel? How many people think they would have a shot at that now? If I ask, are these lines parallel? How many people think they would have a shot at that? Okay, what's the direction vector for the first line? What's the direction vector for the first line? What's the direction vector for the first line?
5, 0,
5, 0, negative 2. What's the direction vector for the second line?
negative 4, 3, 4,
Negative 4, 3, 4. Take the cross product, see if you get the zero vector. You won't. They're not parallel. Now, do this with your arms. Okay. Are those two lines that your arms represent ever going to intersect? Are those two lines that your arms represent ever going to intersect? Yes or no? No. Now do this. Are these two lines going to intersect? They're on top of each other. Are these two lines going to intersect? Yes. So is it possible for lines to intersect in three-dimensional space? Is it possible? It's rare, but it is possible. Now I'm telling you these two lines intersect, and I could ask, oh, what's the point of intersection? And you'd be like, what the hell? Seriously, Dr. Warren? How am I supposed to determine whether or not these two lines intersect? Well, when I say line, you say A plus TD. So let's look at it. If I draw, you draw. I've got these two lines. I'm pretending they're in three-dimensional space, and I'm pretending that they intersect. They intersect at that point right there. And I'm asking, how can I determine whether or not this takes place? Well, give yourself an XYZ axis. This axis would be X, that would be, and this would be
Y.
y. So give yourself one position vector, call that A1, and give yourself a direction vector, D1. Give yourself a position vector, A1, and a direction vector, D1. Give yourself another position vector for the second line, A2, and give yourself another direction vector, D2. Because when I say line, you say
A plus
A plus
T.
A plus TD. Now remember, I just wrapped the rope around my throat. Or try and wrap it around my head. So that you guys would focus. This is where the focusing needs to take place. If my two lines intersect, would there be a scalar that I could multiply times D2, where if I did A plus D2, I could reach that point of intersection? Would there be a scalar that I could multiply times D2, that if I did A2 plus D2, I could reach that point of intersection? Yes or no? Yes or no?
Yeah.
Yes. Would there be a different scalar that I could multiply times D1, so that if I did A plus that scalar times D1, that I could also reach that point of intersection? And the answer would be yes. And that's the trick. That's the trick. So I come up here, I've got my two equations. Let's pick a scalar. If they are going to intersect, and I'm telling you right now, I force these to intersect. There's got to be a scalar that I can multiply times put in for t here. There's another scalar that I can put in for t here, where these two vectors, a plus td1, another scalar, a plus some other number, a plus td2, will point to the same point in three-dimensional space. Now this is the problem. It goes back to high school and solving two equations, two unknowns, which you hate, okay? You hate doing that, especially on tests. So let's pick two scalars. I'm just gonna call one alpha. Does that work for you, alpha? One scalar is gonna be little baby alpha, and the other scalar is gonna be little baby beta. And I'm just gonna plug them in here. I'd say, well then R1 of alpha, if I stretch this out by alpha here, and beta here, would have to be equal to R2 of beta. There's got to be a scalar alpha that I can stretch the first one, and a scalar beta where I can stretch the second one, where these two position vectors would point to the same place in three-dimensional space. Okay, this takes us back to equality. Two vectors are equal if they're, Dr. One, I can't focus at all. Two vectors are equal if their components are equal. Now you guys help me out. R1 of alpha would be, using your space car, R1 of alpha would be
4 plus 5 alpha.
4 plus 5 alpha. Six. And then
7 minus 2 alpha.
7 minus 2
7
alpha.
2 alpha.
But that's got to be equal to R2 evaluated at beta. This has got to be equal to R2 evaluated at beta. Okay, you guys put in the components for the next one. You guys put in the components for R2 of beta. and I'll come back and read it because I know sometimes. 6 minus 4t minus 3 plus 3t minus 1 plus 4t. You guys put in beta. Okay, let's see. Mason, what do you have for your first component? What do you have for your first component?
6 minus 4 beta.
6 minus 4 beta, perfect, thank you, Mason. What do you have for your second component, Roberto? Roberto, what do you got for your second component?
-3 plus 3 beta.
-3 plus 3 beta. And then, Michael, what do you got for your third component?
-1 plus 4 beta.
-1 plus 4 beta. Now you asked Dr. One, where did the alpha and beta come again? Where did these come from? They came out of the thin air. If two lines are going to intersect, and you're going to say A plus TD, there's got to be a T that you multiply times D1 to reach the point of intersection. Call that alpha. There's got to be a T when you multiply times D2 that you're going to reach the same point. Call that beta. So on the test, I would just pick alpha and beta. You could pick whatever you wanted. You could pick ice cream cone and smiley face. I don't care what you pick. I often just pick S and T. I just want two different things. Alpha and beta, though, makes it a little bit easier. Okay. This vector would have to be equal to this vector. This vector's got to be equal to that vector. Well, then 4 plus 5 alpha, 4 plus 5 alpha has got to be equal to, 4 plus 5 alpha has got to be equal to,
6 minus 4 beta.
so let's write that down. 4 plus 5 alpha has got to be equal to 6 minus 4 beta. Well, what else must be true? What else must be true? What else must be true?
6 has to equal -3 plus 3 beta.
Exactly. I didn't catch you as saying that. Thank you. And what else must be true? What else must be true?
7 minus 2 alpha has to equal -1 plus 4 beta.
Perfect. I think that was red. Okay, so Dr. One, what are we doing again? I forget what we're doing. Okay, take the helicopter. Grab your joystick. Fly your helicopter out of Vietnam. Fly up. Okay, now we're looking down. We're looking over the battlefield. What are we doing, Dr. One? What are we doing? Okay, I said, in general, two lines do not intersect. Occasionally, they do intersect. You're looking at these two lines. How many people on Friday would now recognize these as lines? How many people on Friday would recognize these online? And if I said, give me the symmetric form, you'd be like, bam, done, Dr. Warner. Give me the A plus TD form, bam, done, Dr. Warner. Now I ask, do they intersect? And you're like, not done, Dr. Warner, not done. Don't know how to do that, don't know how to do that. And I'm like, okay, well, just stick a parameter into the first one, stick a parameter into the second one, and see if they actually can meet each other in three-dimensional space. Well, that would mean this vector is equal to this vector. Now, this is in general why two lines don't intersect in three-dimensional space. What were the words that just came out of my mouth just a second ago?
This is why two lines do not intersect in 2 and 3-dimensional space.
Because look, there's two unknowns here, alpha and beta. Find me an alpha and find me a beta where these two vectors will be equal. But how many equations do I have? How many equations do I have? 3 equations, 2 unknowns in general sucks. In general, you're not going to find an answer to 3 equations, 3 unknowns. You can find an answer almost all the time to 2 equations, 2 unknowns. And this is what takes you back to high school. Do you guys remember solving systems of 2 equations, 2 unknowns? Do you guys remember doing that? Okay, you shake your head like this, shake your head like this. Because now you're going to do that. No, I'm not doing it, Dr. Yes, you are. You said, I can solve 2 equations, 2 unknowns. My high school teachers did that. So do that. Find the alpha and beta that satisfy those first 2 equations. Find the alpha and beta that satisfy those first 2 equations. You said you could do it. Let's make your high school teachers proud. Find the alpha and beta that will at least satisfy these first 2 equations. 4 plus 5 alpha equals 6 minus 4 beta, and 6 equals negative 3 plus 3 beta. And this is when you're like, oh, Dr. Warren, thank you. You made this simple for me. You made this reasonably simple for me. By not having another t with this 6. Okay, again, for sake of time, I apologize. I wish I had you guys a lot. How many people got beta? How many people have beta? What did you get for beta? What's beta?
3.
3. Once you know beta, can you find alpha? Once you know beta, can you find alpha? And what's alpha? What's the value for alpha?
Negative 2.
Negative 2. It's really, really rare that the alpha and the beta that work here will satisfy the other equation. It's really rare that the alpha and beta that solves the first 2 will solve the third. But in this case, let's just see. If I have 7 minus 2 times the alpha, well, that's negative 2. Does that equal to negative 1 plus 4 times beta? I know it's hard. What do you get on this side? What do you get on that side? 11. And what do you get on this side? 11. So it checks. And in this rare case, the two lines intersect. And you're like, well, Dr. Warren, how could I possibly find the point of intersection? Do you think that's an important problem? Imagine you got 2 beams sitting in 3-dimensional space. Would it be good to know where that point is in 3-dimensional space? You're like, what could I do, Dr. Warren? I'm like, guys, seriously? I mean, think about it. R1 of alpha is equal to R2 of beta. Just put what number into here and you'll have the point. Put what number into the first equation and you'll have the point. Put what number into the first equation and you'll have the point.
Negative 2.
Negative 2. Or you could stick what number into the second equation and you would have the point.
3.
3. So get the point. Get the point of intersection. They do intersect. Get the point of intersection. What is the point of intersection? Now this is really a psychology thing. This is really like for psychology 101. Okay, do you more want to deal with putting the 3 in or dealing with the -2? And this I just want to know. How many people chose to put the -2 in because it was alpha? How many people decided to put the 3 in because they didn't want to deal with the negative? Did anybody do that? Okay, so yeah, I don't know what that means. I don't know what that means. Okay, let me just say, there were a lot more hands for the alpha. There was a lot more hands for the alpha. Okay, so what did you get as your point of intersection? What did you get as the first coordinate of the point of intersection? Where's the point of intersection in my room?
-6.
-6.
-6. So I'm going back. I'm going back into the hallway.
6.
6. Okay, so now I'm going down the y-axis. Running down the y-axis 6. So I'm in the hallway over there. And then how high up off the floor? How high up off the floor am I?
11.
11.
There's my upper point. There's my upper point. So it's pretty high up. It's pretty high up. Now imagine that I don't know why I feel like I just have to keep beating you and beating you. I guess because I'm on a clock. Okay. Now, so I've got these 2 lines. I now know the point. I now know the point is -6, 6, and 11. Would it be kind of fun to know the angle between these 2 lines? Wouldn't that be kind of a fun engineering game? Like, what's the angle? I mean, they're sitting in 3-dimensional space. You're like, well, what is that angle exactly? So stare, squint at it. What is that angle? You're like, Dr. Warren, what is that angle? Ask me that.
What is that angle?
What is that angle? And I'm gonna be, what do you think? What do you think I have black magic? Do you think I have black magic? Seriously, I mean, these are two beams sitting in 3-dimensional space at some wacko angle, and you say, what's the angle between these? Are you out of your flipping mind? What do you think I am, a magician? So you want this, theta. You determine the intersect, now you want the angle between them. You're like, Dr. Wynn, that's impossible. But then I'm like, okay, is a vector the same vector no matter where I move it in 3-dimensional space as long as I don't twist it or make it longer? Is it the same vector? Da, da.
Yes.
Now I'm now one of the Rockettes. Ba, ba. As long as I move my vector, keeping it like this or like that. Is it the same vector?
Yeah.
Yes. So if I take this little direction vector, D2, and I go, whoops, over to there, I take my direction vector D2, and I move it over to there, and I take my second direction vector D1, and I slide it up to there. Is that a legal move? Is that a legal move in vector algebra? Is that a legal move? Then the angle between these is the angle between the two the angle between them is the angle between the two direction vectors. Oh, Dr. Warren, if I only knew how to find the angle between 2 vectors. If I only had a flashcard. That would allow me to find the angle between 2 vectors. If I only knew a flashcard that would give me the angle between 2 vectors. Does anybody remember how to do that? Does anybody have any idea? No.
Would you do,
Cross B equals A, B cosine theta.
That wouldn't be the cross. That sine would give you the cross. What would give you the cosine? Not the cross product, but the dot product. If you have two vectors, A and B, then geometrically A dot B from our law of cosines, this would be equal to the
Norm of A.
norm of A
Beta.
times the norm of b times the cosine of theta. Could you then solve for theta? Could you then solve for theta? Could you then solve for theta? Okay, so write down a flashcard that if two lines do intersect, that would represent the angle between them. Write down a flashcard that would represent, if two lines do intersect, what would be the angle between them if you had to do this on Friday? If you had to do this on Friday. Okay. How many people see what I have here? How many people see what I have here? I have the word if with 3 exclamation marks. If. Because most of the time they're not going to. Most of the time they're not going to intersect. If they do. If you find an alpha and beta that will solve 3 equations with just 2 unknowns, then the line between them, the angle between them, would be what, Caitlin? What do you have? Theta would be equal to the...
I didn't write it with theta, like being equal to it, but
Okay.
I put d1 dot d2 equals the normal d1 times the normal d2 cosine theta.
Okay, I like that. I want to take it a little bit further. And so I would have, if I do d1 dot d2 divided by the norm of d1 times the norm of d2, and then I would do what to both sides to get theta all by itself?
Inverse of cosine.
Inverse of cosine. And that's a nice flashcard to have. That is a nice flashcard to have. But guys, I mean, think how cool this is. Think how cool this is. I mean, I know, you're trying to learn stuff. You have Quest staring at you, scaring you. But guys, you have 2 lines. You guys, you got 2 lines laying in 3-dimensional space anywhere. Holy hell, that's a tough problem. They intersect. What? What's the angle between them? You're out of your mind. No, I'm not. You just need to know you just need to know the direction vector of the first line. You need to know the direction of the second line. Is taking the norm that hard? Is taking the norm that hard? No. Take another norm, just as hard, not hard. Is the dot product that hard? Is the dot product that hard? No. And you just take the cosine inverse of that, and bam, you're done. There's the angle. And that's pretty incredible. That's pretty incredible that we can do this. We're not going to, but let's just see. You guys, I've erased the lines. I'm ADD. I don't have any idea. Does anybody have the direction vector for the first line? What was the direction vector for that first line? What was the direction vector of the first line? Does anybody have the direction vector? Can anybody figure it out for me? What was the direction vector of that first line?
5, 0, -2.
5, 0, -2. I'm believing. What's the direction vector of the second line? What was the direction vector of the second line?
-4, 3, 4.
-4, 3, 4. Now seriously, look at those numbers. Could you take the dot product? Could you take the dot product of those without a lot of effort? Emily, could you take the dot product?
I did not.
No, you don't need to, but could you?
Yeah.
Okay. Could you guys find the norm of this puppy? Could you find the norm? If I gave you a calculator, could you norm it up for me? Could you norm that up for me? And could you norm this up for me? Could you norm that up for me? And then it's just a simple division and cosine inverse. And you've done the impossible. You'd say, hey boss, that angle between those two beams up there, that would be this many radians. And you'd be like, what the hell's a radian? Oh, sorry, man. I'll turn it into degrees for you. I'll change that to degrees for you. Then imagine he gets up there with one of those protractor thingies that they have, like those Bosch ones that'll measure angles, and they get up there and they put that on there, and they're like, holy hell, that boy was right. It is exactly that many degrees. How could he possibly? I mean, they're sitting up there in three-dimensional space like this, and he's telling them how many degrees that is. That's one smart little boy. And you're like, well, really, it's not that bad. It's a dot product. Like, what is that? What does this mean? You're like, never mind. Remember, you're in the 1% club. 1% take Calc 3. 1 to 2.5% of people in states take Calc 3. You're in the 1% club. Okay, so now, one last tough problem, and we're going to call it quits. We got 10 minutes. It's going to take every bit of those 10 minutes. So stand up again, and just smack your face to get yourself awake. Okay, sit back down. This will be the last flashcard. I don't know which one this is, maybe 47, there may be something a little bit after it. This will be the last one required for Quest 2. Okay. This is a really fun exercise because it's just really tough. I've got a line sitting here in three-dimensional space. I've got my line, and I've got some other point that's representing my tape measure. I've got some other point not on the line. I've got my line, and I've got some other point sitting in my building that's not on my line. What I want to do is I want to make a connection to this point to this line. I want to weld a piece of steel from this point to this line. And I want it to be the shortest piece of steel possible. Now I'm going to stick out my tape measure. Does that look like that would be the shortest piece? Does that look like that would be the shortest piece that you would use? Would that be the shortest piece? Now what if I did that? Does that look like it would be the shortest piece? Well, let's see. Does the tape measure, is it going in or is it going out? Is the tape measure going in or is it going out? It's going in, and you can see right about there. I know it's a fisheye, that stupid camera. Right about there is the shortest distance. And what is maybe a little hard to see is we're making a right angle between the line and the tape measure. I'm making a right angle between the line and the tape measure. Now we're going to draw that so you can write it down on your piece of paper. We're going to do the same thing, but we're going to draw that so you can write it down on your piece of paper. So give yourself an XYZ. know why I like doing this? I like putting me down here on the ground at the origin. So I draw myself a little buddy, my little buddy, that's me. Give myself some arms. So there I am, I'm sitting there in the room and I'm looking up and I'm looking at this line, and then I'm looking at some other point and I'm like, I wonder what the shortest distance between those are. So now, when I say line, you say,
A plus TD.
so let's give ourselves a position vector, A. Let's give ourselves some direction vector, D. And then you guys draw the line. You guys draw the line that if we let that scalar t, a plus td, that scalar go from minus infinity to infinity. You draw the line in the classroom. You draw the line in the classroom. Okay, I'm hoping everybody did that. Okay, now let's pick a point not on the line. So I'm imagining it's back behind the chalkboard. I'm imagining it's up above the line, but back behind the chalkboard there. And I'm trying to find, maybe I'll even move it up here like that. I'm trying to find the shortest distance between that point in my line coming out like this. So I know I want it to be like, again, I'm imagining it being back there. So it's kind of at a right angle coming back to there. And I'm trying to find out what that distance is. I want to find that distance to go tell somebody to cut that and then go up in the air and weld it. And more importantly than it's the shortest distance, that if you're engineering guys, it's a right angle. That's going to create a lot of support there at that joint. That's going to create a lot of support. You know it's at a perpendicular angle. It's going to carry that load if it's coming in that direction. So this is my point. So give me a point, guys. Give me a point. Anyone. This is not a hard question. Give me a point. Point. Some of you guys just like, Caitlin will answer. 7, 9. We're in 3D. We're in 3D. 18. So you did it. Okay. I've got another point here. If I gave you the point, could you get a position vector that would run to that point? Like if I said, oh, what's the position vector that would run to Caitlin's point? 7, 9, 18. How many people could find a position vector that would start at the origin and then go to that point? What would it be? What would the position vector be? Dr. Wunsch, stop it. What would it be?
7, 9.
Oh, that's not that hard, Dr. Warren. So draw a position vector that would start at the origin and run to that point in three-dimensional space that we have. Draw a position vector and mark it as B. Draw a position vector that would head to that point in three-dimensional space and mark it as B. And I'm going to do the same thing. I'm going over top of my line here, going back into that behind the chalkboard, and I'm marking that as B. So I've marked that as B. Do you guys have your same vector? Do you have that same vector? Now, for sake of time, I wish I could give you guys a half hour to play with this question, because you guys could get it. Eventually you would get it. I'm going to write it down, and then it's me giving it to you, which is not near as much fun. Now again, imagine you got this line, and you got this point, and somebody poses this question to you, and you're like, this is tough. This is a tough question. But I'm willing to bet, if you're doing vectors, I'm willing to bet somebody in the classroom of 26 of you here, you would say, okay, well, let's draw that vector. How many people think that might happen? How many people think that could occur? And you're like, well, I really want to know that perpendicular distance there, but I'm not quite sure how to do this yet. I've got this vector A, I've got my vector D, and I've got this vector B, and I want to know that perpendicular distance. 10 minutes from now, somebody would draw this vector. And what's that vector? What's that vector? If this is A and this is B, what's that vector?
B minus A.
B minus A. So mark it as B minus A. Now this is the thing where it's a little hard to see. It's a little hard to see. Oh, let me do this. I don't know if I can land this plane and do this at the same time. So I've got this point up here. This B vector's here, guys. This B vector's coming like this. It's not intersecting my line. It's not intersecting the line that I have here. It's above the line. It's not intersecting the line. It's above the line. It's flying over top of this line. This vector, however, is intersecting the line. It's starting at A, that point on the line, and connecting the point P there. This is creating a right triangle. This is creating a right triangle where one part of it's on the line. This goes to the point here, and this connects there. How long is this hypotenuse? How long is the hypotenuse of that right triangle?
B minus A, or the norm B.
The norm of B minus A. Now this is where we're going to, the norm of B minus A. Imagine this is the angle theta. Imagine this is the angle theta, then what would be this distance? If this is the hypotenuse and this is theta, what would be this distance? This goes back to trig. If you know an angle and you know the hypotenuse, what's the opposite side? What's the opposite side?
Norm of B minus A times sine theta.
Norm of B minus A times the sine of theta. Okay, now, I gotta let you go. I'm going to give you the flashcard. And then I'm going to explain it on Wednesday. I'm giving you the flashcard, and then I'm going to explain it on Wednesday. I've got a vector B minus A and D. Theta is the angle between them. I want the norm of B minus A times the sine of theta. If you take the norm of B minus A, and you cross it with D, take B minus A, cross it with D, and take the norm, and you divide it by the norm of D, you'll end up exactly with this distance.
What does D represent in that problem, that vector?
You tell me, what does D represent in the problem? When I say line, you say
A plus C.
A plus TD. So what does D represent
The
in
direction vector.
the direction vector of your line? Very good, Gordon. The direction vector of your line. What does A represent?
Position vector.
Position vector. What does B minus A represent? Tough question. What does B minus A represent? The vector going from the tip of A to the point P in three-dimensional space. Okay, we'll pick up with this on Wednesday. That's the last thing that will be on the quest. That is the last thing that will be on the quest. This was a tough day, guys. This was a tough day, picture-wise and a lot of stuff. But you guys did well. You did well. Okay? But you've got to do your homework or you're going to get slammed like by a Tonka truck bulldozer on Friday. You've got to do your homework. You've got to do your homework. What did I just say? You can leave with this. What did I just say?
You gotta do
Do
your.
your homework.
Okay. See you guys. Thanks for putting up with me.
Thanks, Dr. Moore.
Thanks, Dr.
Thank
Warren.
you.
Have a good day.
Thank you, Dr. Moore.
I'll clean up my mess. Oh, and thank you guys for putting up with me too. Stop.